Hello. It seems the doors have been closed, so that's our signal to get started. First of all, welcome to this session. I hope everyone is having a good time in TechEd. Because I haven't. It was quite a stressful situation backstage. I will tell you why in a moment. But before we get started, a brief introduction of myself. My name is Haishi Bai. By the way, Bai is a last name in Chinese. It doesn't mean I'm saying goodbye. It's just a last name. Actually, it means white. Okay. This is my second year with Microsoft. And before I joined Microsoft, I've been working mostly in Silicon Valley for different companies on different projects for about 15 years. So I'd say I've seen a fair number of projects, and I've been involved in quite sizable cloud-based applications. But talking about architecture is still, how do I put it? It's still risky. Because whenever it comes to architecture, people intend to have very different and very strong opinions. And I don't know how many of you have been in the situation that you are having a heated discussion with your colleagues about architecture. Anyone have been in that situation? Yeah, I've seen hands going up. Anyone actually punched anybody in the face? Okay. I didn't either, but in my mind, I did it in my mind. So, as I said, talking about architecture is always risky, but I think this kind of session is useful. I hope through this kind of session, we can give you some ideas and guidance, and at least some information so you can make informed decisions when you design your own cloud application. But just to clarify, I'm talking about architecture in general. It's not about your specific project, so I'm not discussing with you. And if you have questions, please hold it till the end of the session, because we do have a lot of contents to go through. And tomorrow evening, I think there's a Ask the Experts session happening tomorrow night or Thursday night. I will be there as well, so you're welcome to stop by to have more discussions if you want. So let's get started. Today, we actually have a very simple schedule. First, I will talk about why cloud is different, why we want to design a different architecture when we design cloud applications. Then I will dig into three important aspects: fail-safe design, scale, and integration. These are not all the topics we should cover for the cloud designing, but these are three important ones. I think if we have sufficient time, we may talk a little more, but these are the three major topics we'll focus on today. Then the last, we'll save about 10 or 15 minutes to do a couple of demos. I'm going to show you some of the new features provided by Windows Azure and what you can use in your own project. So that's the plan. Let's get started. First, let's talk about why cloud is different. Here I'm going to show you a couple of quotes from anonymous sources. Basically, these are common misconceptions. Actually, I should stay behind the table, because this morning I just realized my pants are not growing as fast as my legs. So I'd rather stay right here. Okay. So some common misconceptions. The first one, actually this one, I said it many times myself. I don't know if you've said it. That's a hardware failure, not my problem. I've been an engineer for quite a few years, and I've said that in many occasions with relief, because that means my software is perfect. The system failed because there's some hardware failures, such as the disk failed. That's really nobody's fault, right? The disk failed, what you can do? You have to restore the server. That's nobody's problem. However, on the cloud is different. You cannot say that anymore. Because on the cloud, the virtual machines you get from cloud platforms are running on the commodity hardwares. Those are not like top class, expensive hardwares. And they will fail. They will fail. And even they don't fail by themselves, the virtual machines might be brought down by the cloud platform for maintenance, such as applying important security patches, so that to take that offload from you, but on the other hand, you need to prepare for failure. So this is very important to remember that on the cloud, hardware failure is not an exception anymore. It's a norm. It will happen. And your application has to be prepared for that. Because your customer doesn't care if it's a software problem or hardware problem. They want the service to be available. If the service is unavailable, that's too bad. They will complain to you. You will lose business. So you have to prepare to failures. The second one, let's throw more memory into our database server. I've done that many times myself as well. I'm not mocking this method. This is a very valid method to solve some of the bottlenecks because it's cheap, it's fast, it's low risk. But on the cloud, you cannot scale up all the time. Even for the physical machines, even on the on-premise system, you cannot just infinitely increase the memory on the machine or replace CPU on the machines. You have a hard limit. Oh, something's dragging over there. And on the virtual machines, the virtual machines you get from cloud vendors are even more limited. Basically, you have a list of options, but you run out of options pretty quickly. Windows Azure just added 2 more levels. We have now A6 and A7, in case you haven't heard about it. So basically, with A7 instances, you can go as high as 8 cores and 56 gigs of memory. That's pretty large, but you cannot go beyond that. So when you hit the limit, you have to scale out your application. What's more interesting is that if you are subscribing to a service, when you subscribe to a service, all you get is the endpoint to that service. You're not getting machines back. You cannot throw memories at it. You cannot throw anything at it. If your calls are throttled, you have to figure out other ways to work around that limitation. The next one. Our service is 99% available because we are using Azure. That should be a true statement, isn't it? Doesn't Azure promise us all those nines? Actually, it's higher than 99.9. It's 99.95, 99.99. And our application is only using the Windows Azure services. So we should be able to promise our customers that our service is 99.9% available. However, that's not the case. And in a moment, we'll explain exactly why you cannot make that kind of promise. And this is the scariest one. Actually, I think I just heard about this statement again last week. Running out of capacity, that's a good problem to have. Actually, if you think about it, running out of capacity is a problem, but it's never a good problem. When you run out of capacity, that means you could have served more customers, but you didn't. You could have earned more money, but you didn't. Your customer could have been more satisfied, but they weren't. So running out of capacity is a problem, but it's not a good problem. But the scariest part of this statement is that when somebody is saying something like this, that means they are not thinking about scaling at all. Maybe they've heard that cloud is a scalable platform. That's a true statement. Cloud is a scalable platform, but that doesn't mean your application on the cloud is scalable. Scalability is not automatic. Not only you need to design for it, you also need to plan for it. And we'll explain how in a moment. The next one, we'll move everything to cloud. Isn't this what Microsoft wants? Isn't this what Google wants, what Amazon wants? Actually, I don't know, is it recorded? Okay, I'm going to say it anyway. I believe, actually, this is exactly what Amazon and Google want. Why? Because they have nothing on your on-premise data centers, right? But for Microsoft, it's totally different. We acknowledge an enterprise is made up of hundreds of applications. You have a lot of legacy systems. It's just impractical to move everything to the cloud. Even if you set the course to move everything to the cloud, that process will take a long time. Months, years, decades, who knows? So when you design your application, you have to be ready that your application will need to work with on-premise systems. And Microsoft provides a very unique and comprehensive solution for you to build what we call the hybrid cloud, that you can not only to make your cloud service on Windows Azure and your on-premise system work together, you can make the transition. You can deploy your application on the cloud, on-premise, and because your application is your logical unit. It doesn't matter where you deploy it. You should get the same level of service. We are not totally there yet, but I think we are way ahead of other competitors. Designing for the cloud. As we talked about those differences, let me just give a brief summary of what we are going to talk about today. First, we'll talk about fail-safe. Again, things will fail. It's not a hardware problem anymore. It's a problem of your application. You need to design for that. Second, scale. Scalability is not automatic. If you only get one thing out of this session, maybe that's one of the candidates. Scalability is not automatic. You have to design for that. You have to plan for that. Integration. Your application will need to work with on-premise systems. You have to design for integration. So let's just jump to the first one, the fail-safe. Why we want fail-safe? It's simple. We want availability. We want our service to be available. Because if there's no service, there's no money. And let's just review some of the basics of availability. Availability equals uptime divided by uptime downtime. So for any given period of time, the more uptime you have, the higher availability your system has. It's straightforward. And to achieve high availability, there's no magic. We have to use redundancy. So with redundancy, we can actually achieve higher availability by introducing redundant resources. This is an example. For instance, in this system, I have 3 servers. Each server provides 90% of availability. But when I put them behind the load balancer, the whole system fails only if all 3 servers fail at the same time. So in this case, by simple math, my system actually can achieve 99.9% availability. And with the same machine spec, if I introduce the 4th machine, I can reach 4 nines. But the point here is that availability is not free. When you introduce redundancy, you need to incur more cost. You need to get more resources allocated. So before you want to promise those nines to a customer, you want to ask yourself, do I really need to promise those nines? Here I'm going to give you an example about the difference between 3 nines and 4 nines. Let's say if a system is available 99.9% of the time. That translates into about 10 minutes of downtime each week. But if a system is 99.99% available, that translates into about less than 2 minutes downtime per week. So will your customers really care about that 8 minutes of difference? Can you go higher? Because you can go higher, you can save money on the resources. So before you promise those availabilities, you need to ask yourself, do I really need to go that high? Because whenever you promise more, you have more liability on yourself. Does that really worth it? And here we will answer the question that if you have subsystems that have a high availability, will the whole system be high available? Most of the systems are made of multiple subsystems. And by the rule of composition, your availability actually goes down. Here's an example. I have 3 systems. Each subsystem provides 99.9% availability. What's the availability of my whole system? Will it be the average of the 3? Will it be the minimum of the 3? Actually, the whole system works only when the 3 systems are working at the same time. So my availability is actually 99.7. It's not 99.9. Actually, your system availability will be lower than the lowest available component. Yes. your system availability will be lower than the lowest available components. Let's say you have all the other components with 99.9% availability, but you have one component with 20% of availability. Then your whole system cannot go beyond of 20% availability. So before you promise those nights, you have to ask yourself, can I really reach those nights? And Windows Azure just happened to be is a highly available system by itself. So we should be able to learn from Windows Azure how it's designed, how it's using redundancy to provide high availability. Actually, there are quite a few points we can review. The first one, the storage. Windows Azure storage saves 3 copies of data. And if you turn on the geo-replication, we save 6 copies of data so that you have redundancy in your data layer. And the SQL database, that was called SQL Azure. SQL database, when you provision a new instance, we actually have 3 servers back up that instance for you. So if the primary service fell down, we still have backup services. Windows Azure caching. When you use Windows caching cluster, you can turn on the high availability option, which means your data will be saved twice on different nodes of the cache cluster, so that if one of the nodes fails, you can still get your data from the other node. Of course, I think everybody knows this. When you deploy a website or cloud service on Windows Azure, you can have multiple instances for scaling as well for redundancy. And you can do the same thing with virtual machines. Not all the people know this, but you can actually join the virtual machines into the same load balancer and provide redundancy. And there's a built-in redundancy in Windows Azure Virtual Network gateways. So when you provision a new Windows Azure network, the gateways we provide to you has a built-in redundancy so that we can provide a very high available connections between your virtual network and your on-premise network. And at an even higher level, if you have multiple deployment across different data centers, you can use Windows Azure Traffic Manager to set up even either a load balancing rule or a failover rule, which means if the primary data center crashes because of some like a big disaster, you can reroute your user traffic to a backup data center. So you can see there are many things that Windows Azure provides you to achieve high availability. But that's only part of the story. The other part of this story of fail-safe design is about the reliability. Here again, we are going to do some really quick review. Basically, this is a review of computer science, whatever course. So my system is available at the beginning, then it fails, then it takes some time to be repaired. And statistically, this is called mean time to repair or mean time to recover. Then the service is running again before it fails again. That's the mean time to failure. And there's another measurement we can use to measure the reliability, but we'll ignore that for now. So why I'm saying this is that because on the on-premise system, the way we increase reliability of the system is to focus to make the mean time to failure longer. Why we do that? Because on the on-premise system, the mean time to repair is really long. Let's imagine if your hardware failed, you have to place the purchase order, you have to install the new hardware, test, and bring it online. So that time is very considerable. Let's say your primary system fails, and you need this much time to fix the system. So your backup system has to be maintained healthy long enough so that you can fix the primary system. This is why this is kind of chicken or egg problem. Because it takes longer to repair, you need to keep the system running for a longer time. So this is very expensive and complex to do. On the cloud, we are actually taking a totally different approach. So instead of focusing to make the mean time to failure longer, we are trying to make the mean time to restore shorter, as short as possible, in the term of minutes, so that when your service fails, it can be quickly restored. In many cases, without any actions from you. So in this case, we are increasing the system reliability by shortening the mean time to restore, and we don't require to have a very high-end hardware to support the longer mean time to failure. And you can see this principle is used and, across Windows Azure, and a lot of those features are available to you as well. For instance, the auto recovery. When you deploy a service instance to Windows Azure, if it fails or if it doesn't respond to the health probe, we will recycle your role. We'll recycle your role, or if the machine failed, we'll allocate a new virtual machine and deploy your service and restore your service automatically. You don't even need to do anything about it. And the fault domain. Basically, in the data center, we have those huge racks of servers, and each rack has its own power supply, cooling supply, network interfaces. So basically, each rack is a fault domain. For instance, if the power failed on that rack, all the servers will go down on that rack. But by using the fault domain, you can instruct Windows Azure to deploy your services across different racks, so that even if one rack goes down, you still have instance on the other servers. And you can do the same thing with virtual machine. If you directly provision virtual machines, you can use availability set to allocate virtual machine across different fault domains as well. And when we upgrade your service, instead of taking down your instance all at the same time, we actually do an upgrade domain walk, which means we'll take the instance down group by group, so that as we are upgrading your group of instances, you still have other instances serving for your customers. And we support multiple deployment environment. We have staging environment and production environment, so that you can deploy a new version on the staging environment, doing tests, and once you are satisfied with the version, you can do a VIP swap to promote the staging to production, and your production will be becoming the staging environment for the next version. So it just goes down, go on in parallel. And also, to reduce the mean time to restore, we provide a very comprehensive diagnostic and debugging support. Actually, at the end, I'm going to show a demo of one of the new features we provide in Visual Studio. So at the first, we have a simulator. Basically, we can simulate the basic cloud environment on your local machine. That's quite unique, and that's quite powerful, which means you can locally debug your cloud services before you deploy to the cloud. Everything is local. You can trace, you can step through, you can do everything, just like a local program. And we also have IntelliTrace, which allows you to capture and play back server states on your local machine. Basically, if the error happens, you can get the IntelliTrace file, and you play back in your Visual Studio, and you can actually trace what the errors are. You can see the details of exceptions, and you can even see the context when the function is called. You can see the parameter to the function. It's really powerful. And we keep improve our diagnostic capabilities. Like I said, I will show you a brief demo after this. And of course, we have first-party and third-party support of telemetry. We have management API, management portal, performance counters, diagnostic data, and you can use third-party tools which you can buy from the Windows Azure store, such as New Relic and App Dynamics. You can collect all those telemetry data and monitor your service health. And last, I mentioned that I will talk about this in the next slide. We also provide transient fault handling application block for you to handle transient errors. We will talk about transient errors in the next slide. So that's what Windows Azure provides you out of the box. And what does that mean to you? What do you need to do to design for the fail-safe? It depends, of course. I mean, every project is unique in its different ways. But we can abstract some of the general practices. So the first one, take advantage of those features. We just talked about 20 of Windows Azure features. Make sure you take advantage of them. Avoid single point of failure. I don't think that this one needs too much of an explanation. You need to build redundancy across all your layers. It's not sufficient just to build redundancy in your application layer or just in your database layer. You need redundancy across all your layers. Otherwise, that component will become a single point of failure. If it goes down, the whole system goes down. Failure mode analysis. Actually, the reliable engineering itself is a very large topic, but this is one of the general practice you want to do when you engage in the reliable engineering. You want to do the failure mode analysis. You need to analyze your code to see where it may fail and how you will deal with it. Transient errors. So for those of you who don't know about this, transient errors means those temporal errors that may happen once, then when you retry, it will be okay. So there are many different reasons for transient errors. Maybe because of a network problem, or maybe just because the service is throttling your call. Transient errors can occur anytime. You cannot predict them. And the way to handle those errors is to retry. I mean, no matter how simple the method call is, let's say if you are using a service bus queue, you're calling the method to say if the queue exists. That's a single method call return a Boolean value. That call may fail because of the transient errors. So to make your code reliable, you really need to put a retry logic around those calls. But you can imagine if you put all those retries in each line of your code will be really hard to read. So that's why the Microsoft patterns and the practices, they provide this transient error handling application block, which allows you to define your retry policies and to write a really clean code with the retry logic in it. For instance, you can define a policy to say, I want to retry this method at like a 1 second interval, or I can try the first failure. After first failure, I will try after 1 second, then after 2 seconds, then after 4 seconds. So you can progressively step back. So make sure to check out that application block. And graceful degradation. This means this means when some of your subsystems are down, instead of stop providing services, you try to keep your service up, but maybe with limited functionalities, because you don't want to lose business. I'm going to give you an example. Let's say we have an online ordering system. So the online ordering system has two subsystems. One takes order and the other processes order. Let's say the second subsystem goes down. What do? Instead of stopping to serve your customers, you should still take in orders, right? We still want that business. But as you take in the orders, what you can do is to inform your customer that your orders, you can still place your order, but your orders will be processed at a later time. So this is what we mean the graceful degradation. Actually, for most of the online ordering system, because of the purchase orders usually takes days or even weeks to be fulfilled, maybe that several hours of difference doesn't matter to your customer at all. So with graceful degradation, you are keeping your service available. That's another point when you promise those nights to your customer. You are keeping your service available. Your service didn't go down, although your subsystem may have failed. Eliminate human factors. Humans are very smart and creative creatures, but humans are extremely unreliable. Although we may have the knowledge, but maybe we are just in a bad mood, or maybe we're just getting lazy, or we're just spaced out for no reason. Yeah, that was me spacing out. So I hope I made the point. Human is very unreliable, so you should eliminate human factors as much as possible. Automate whenever you can. Whenever you see a chance to automate something, some process, you should do that. Now we can come to the next topic, scale. So to make the topic a little easier, we first review some of the basics. So just to warm up. Scale, we often hear about scaling up and scaling out. The so-called scaling up, which means to increase the utilization of your existing resource. Let's say here I have one instance. I can use parallelization, multi-threading to make higher usage of my resource. Or I can buy a bigger machine, subscribe to a bigger virtual machine to gain more throughput. But there's always a hard limit, right? When I reach that instance capacity, I cannot go higher anymore. In this case, I have to scale out by adding more instances. But here's the tricky question. Can I just go up like this infinitely? Maybe, okay? Actually, that's a good answer, maybe. But you cannot do this just automatically. Because when you scale out, you're building up more and more servers. But your servers always have some kind of a dependency to some kind of service, like a database or external services. And those services will throttle you. You cannot just go on forever, right? So in this case, if you keep adding more instances, you're not gaining more throughput because you are having a bottleneck in your system. The way to deal with this is to segment your work. Basically, you have to plan to segment your workload into multiple service entities. For instance, you can use multiple queues, multiple topics, multiple storage accounts, multiple database, or even multiple Azure subscriptions. Because no matter what you do, there is a throttling limit. So if you want to go higher than this red line, you have to segment your workload. Then you can actually keep going. Yeah, and like I just mentioned, not only you need to design for scaling, you need to plan for scaling as well. So what we used to do on the on-premise system is that when we prepare for possible workload changes, we prepare for the worst case. Why? Because provisioning new resources on on-premise data centers is really long process. It takes weeks or even months to buy a new server. So in this case, we have to prepare for the peak. That means, hey, we have sufficient throughput to handle those workloads. But of course, in this case, there are a lot of resources wasted. They are just sitting idle most of the time. On the cloud, it's totally different. Instead of preparing for the worst, we can actually identify what we call a scaling unit. Basically, I'm saying instead of preparing for the most possible peak, I'm going to identify a scaling unit, which defined as to serve this number of customers, I need this number of servers, this number of queues, this number of storage accounts. And as my workload changes, I can just scale up and down those scaling units to adjust my throughput. However, this is you cannot do this reactively. Let me try to move the mouse pointer here. You see the yellow line above the white line here. That means your system already running out of capacity. So when you detect that and try to scale up, there will be a lag because although scaling up is fast, but it's not instantaneous. So to deal with this situation, you have to do some kind of prediction. In other words, you have to be, ignore that. You have to be able to shift this curve to the left so that you feel your system is about to go out of capacity. You have to scale up beforehand. This is not always easy to do. This requires you have quite accurate measurement. This requires you have quite accurate prediction of the workload change. And there will be a lot of scaling up and scaling down operations. So what we usually suggest is that to design a larger scaling unit. So instead of like changing your scaling unit per, let's say, 100 customers, you design a scaling unit for 1,000 or even 10,000 customers. So in this case, you don't need to do the scaling operations that often, and you can still satisfy your workload changes. scaling in Windows Azure. And in case you don't know, Windows Azure happens to be a scalable system as well. So let's see what Windows Azure is doing to achieve scalability. Of course, you can scale up by using different VM sizes. You can scale out by adding more instances. You can use auto-scaling application block to auto-scale your application. And you can use data sharding to shard your customer data into multiple Azure SQL databases. And here, this is what I just talked about, the way to segment your work. You can use multiple service entities, like queues or storage accounts, to segment your workload into multiple service subscriptions. And we have CDN, the Content Delivery Network. Basically, you can cache your content, especially static contents, onto the CDN nodes so that those customers can be served directly from the CDN nodes instead of going back to your server. So this is not only give you the performance benefit, it also helps you to scatter your user traffic to those CDN nodes so that with one server instance, you can actually achieve higher throughputs. You can use caching to offset some workload. For instance, if you decide your database is becoming a bottleneck, you can use caching in your application layer so that you don't go back to the database and do a repetitive query that often, so that you can solve that bottleneck and achieve higher workloads. And that's what Windows Azure provides out of the box. And what do you need to do to design for scaling? Again, it depends, because each project is unique. I'm just going to say it one more time today, but some general practices apply. First, as we said, you need to design for your capacity. You need to design for scaling. You need to plan for scaling. So cloud is not killing the IT pro's job. IT pro's job is really oriented to provide even more values. You need to design your system so that it scales well to serve not only 100 customers, but 1 million customers. Proper decomposition of system. This is too big of a topic to discuss in detail. Basically, in my opinion, that's the number one job of an architect. The number one job of an architect is to properly decompose the system, to identify what are the components, and what are the connections among them. Only you achieve this, you can scale your different parts of your system independently. Let's say you are identifying your data layer is a bottleneck, you can scale out the data layer separately. But if you have a strong dependency between your application layer and the data layer, the scaling of the database layer may have side effect on the application layer. For instance, maybe your application is not designed to take in the additional workload, right? Things like that. Stateless design. The most scalable components are stateless, which means each request can be handled independently. It is not affected by any requests before or after it. In this case, your workload can be actually easily distributed to all your instances, and we can scale out to add more capacity without affecting existing instances. But we do realize that not all the systems are designed in this way. Designing a totally stateless system is not necessarily that easy. So I'm going to talk about how to transit a very stateful system into a stateless system in the next slide. And scale at all layers. I don't think I need to explain this. You need to scale all layers. Otherwise, the layers you don't scale will become your bottleneck. Throttling. Throttling means, well, actually, scaling means how many customers you can effectively serve during a period of time. But you always have limited resources. So how to make those customers to effectively share your resources, you have to throttle. You cannot afford that a single customer generates a really heavy workload and kill your whole system. So you have to play fair and make sure all the customers are within their quotation. And here, let's talk about the designing of the stateless system. Like I said, we can roughly categorize system into 3 different types. stateless, shared states, and global states. The stateless system is really easy to be scaled out. Basically, because each request is handled independently, we can easily have more instances to handle more requests, no problem. The shared state system, they have this notion of a session. For instance, a shopping cart. Right? When the user has a shopping cart, the request has to go with the same shopping cart, otherwise he's shopping for somebody else. For this kind of system, it's not that hard to change it to stateless. All you need to do is to separate your state and your requests. And there are easy ways, especially for the web requests. You can use external state storages, and I will talk about one in the next slide. But on the other hand, even if you don't do this, if you don't separate the state and your actions, you can still scale out by sessions. Basically, you have sticky sessions or server affinity, so that each user, when it opens a session, all the subsequent requests is handled by the same instance. You can do that. I mean, you can still scale your system basically by the user sessions. The hardest one is the global states. Global states, although here I can draw a diagram to show that there's some component that knows about all the requests, but in reality, it's really hard to draw a diagram for this kind of system. Usually, this kind of system has a singleton instance that assumes it has the global knowledge. I've been trying to think of a good example without referring to any political concepts, but here I'll just make up someone. Let's say you have a dispatching system, right? You have a bus dispatching system. You have a dispatcher to dispatch buses to different routes. And now suddenly you have more buses to handle, and you have two dispatchers. And if these two dispatchers each assume they know about all the buses, you will have this situation that two dispatchers are sending the same bus, the bus is lost somewhere. So this kind of a system is really hard to be scaled out, but it's still possible, but you need to do some more work. The way to scale this without any code change is to add some kind of a routing mechanism in the middle. Basically, you are scaling by customer, by tenant. Let's say you still allocate a dedicated server for customer A, another server for customer B. You can still do this, but you can see the flexibility and the real scalability is really low in this case. So what we suggest is you to make those transitions. First, to eliminate the global states. Those components are bad, regardless if it's in cloud or on-premise. Then from the shared states to the stateless, it's just a matter of separate the state and actions. And there's two basic options you can use. The first, you can externalize the state. For instance, we have a cache session state provider. That's a really long class name, but it works. Basically, it's an SPNet session provider. If you use SPNet sessions, you can just configure this provider with an SPNet application. Then you just operate on sessions as you were. Then this session state is saved outside your SPNet process, so you can have a stable shared session. And the other way this requires you to change the architecture of the system is to separate actions and states. I'm not saying this is the only way, but this is a feasible way, which is to use a job queue. Basically, you're centralizing the states into jobs, and their job creator and their job handler are essentially just action executors. They don't have states themselves. The job is carrying on their own states. And integration with on-premise system. That's the third topic. Let me do a check on time. I think I'm doing just right. Okay. Integration with on-premise systems. And here I'm going to tell the story why I'm so stressed this morning. So I don't know if some of you may have noticed on the title slide, I have a second speaker, Mr. Here, Yes. Suddenly the name skipped my mind, I'm sorry. But see, the human is not reliable. But basically, he's from Argentina, and he brought in a very nice demo. You know the gas pump controllers you see in the gas station? What their company does is to integrate those old gas pump controllers with Windows Azure. I mean, those devices are really old. It's like 10 years old. They are not designed for cloud. They are not even designed for network connectivity. But they did some amazing job to integrate those systems into Windows Azure. What happened is that because the system is shipped from Argentina, when it passes the custom, there was certain inspections going on. Basically, the machine was torn apart. All the boards were pulled out. It was dangling everywhere, so the machine was essentially broken. So this part, original my plan was to do a demo, just talk about the integration. But this is my plan B, so I'm just going to go through the slides. So this is a failover scenario in real life. So integration, I don't think we should go through this diagram, but the key point is that not all the system or all the workloads should be migrated to the cloud. Before you embark on a project to migrate something onto the cloud, you need to ask yourself, does it worth it? Can I actually do it? First, you have to be clear why you want to move to the cloud. There has to be some goals. You cannot, well, if you just want to have something nice on your resume, that's a different story. But that's also a goal, right? You have to have some goals. Then you have to estimate how much effort I need to take to achieve that goal. And does it worth it to take that? And because the on-premise system, they are interlinked with each other, you have to analyze what kind of impact, not only at technical level, but also at business level. And this is very important for a lot of, I could say, technical guys to ignore, that when you migrate something from your on-premise to the cloud, you're potentially changing your business workflow. This is a big deal. This is not only within your IT department. This will impact your whole business. So before you do that, you have to answer those questions. So, but the reason I'm showing this diagram is actually I want to show the red dot, which means not all the workloads and systems should be migrated to the cloud. That's why we need integration. And general integration strategy, I think I'll just skip this one because this one should be really straightforward. Usually, how do we integrate different systems? We use data. We use shared data. We write to the same database, or we do the data import, export to integrate, or we do the direct invocations. We expose the API from one system and we call from the other, or we use some middleware like BaseTalk or whatever to facilitate your integration. And as far as the topology of the integration, we can have direct connections. We can have the hub and spoke architecture. Of course, the hub and spoke, it reduces the number of connections, but on the other hand, it introduces a single point of failure. And that's why a lot of people, this is not me saying, but a lot of people in the industry, they prefer to use a middleware like a service bus, enterprise service bus, to integrate the system. Although on the diagram, the service bus, this guy in the middle is still one piece. But in reality, it can be implemented as a distributed system with high reliability and availability. So although on the diagram it may seem the same, but actually underneath the principle is rather different. But that's not the main point I'm going to discuss today. So we'll see how Windows Azure help you to achieve those integration goals. We have message-based integration. We have Windows Azure Service Bus. We have queues, topics, all those wonderful notification support. You can achieve message-based integration easily. And we also provide you connectivity support. The Windows Azure network or virtual network. I'm going to show a diagram of the Windows Azure virtual network in a moment. So basically, that provides you a very strong connectivity between your Windows Azure machines and your on-premise machines. And when we talk about integration, we have to handle the problem of authentication and authorization. And in this area, Windows Azure is quite unique because we have Windows Azure Active Directory, which allows you to integrate your on-premise Active Directory credentials with your cloud credentials. And we also have Azure Access Control Service to provide a single sign-on, not only with the Active Directory users, but with other social network users like Facebook, Google, or Yahoo, or whatever have you. And also, the Windows Azure system is more open than ever before. We have a very inclusive ecosystem. Not only you can use .NET and Windows, you can use Linux, you can use Node, Java, PHP. I think now we are adding Ruby as well. And Windows Azure is embracing all those standards. We support RESTful APIs over HTTP. We support OAuth, OData. Actually, that's one of the Microsoft started standard. And WS Star, such as WS Federation, WS Security. And what does that mean for your application? Okay, there it is. So that's the last time I'm going to say it. It depends because each project is unique, but there are some general practices. Loose coupling. When your system are interlinked together, it's really hard to change or really hard to migrate anything. So if your components are loosely coupled, you can easily just take them apart and host them in different environments. Minimum exposure. That means when you expose the interface, you should minimize the information or the complexity you expose. Because the more you expose, the more people will take use of it. Then when you make a change, it will be really hard to change those components without affecting dependent components. Integration isolation. Actually, this is a term I cooked up. I don't think it's a good one. But what I mean is that when you integrate with other systems, you should try to isolate the integration code in a central place. Let's say you are integrating with this machine. You should have a repository, maybe a proxy that handle all the interaction with this system, so that when you switch to a different system, you can easily switch it out without affecting the rest of your system. Secure by default. And I've seen this many times because the two companies have a very strong partnership. And they're saying, hey, just send me a text and I will deal with it. But then the requirement will change. Hey, how about we do this over internet instead of intranet? How about we do with other partners? So when you integrate with other systems, the general principle is that it's secure by default. You should employ either a transportation security, like using HTTPS, or use message level security, such as encryption or signature, so that you can securely talk to other systems. And use standards. More and more people are using standards nowadays. Should you, in case that if you implement some standard interfaces, other customers may be able to integrate with you without you doing anything. Let me check on time. Okay. And let me just say a little more words about message-based integration. So here I'm basically assuming you're using Windows Azure Service Bus, and you have 5 systems to be integrated. Instead of directly invoking each other, what you can do is to create a job queue so that your system can generate some jobs, and these jobs will be consumed by other systems. And you can use topics to broadcast the job to other systems. So the key difference here is that for the queue, System B and System C are actually competing for the job. So only one of the systems will get the job. But in the case of topics, both System D and System E, they will get their own separate copies of the job. So that's the difference. One gets it or both of them get it. And when you use message-based integration, because it's a very flexible architecture, you can easily extend this architecture without affecting running system. For instance, now I'm having a system F. I can just add a subscription to my queue, and my existing system don't even need to know about it. It just appears online. It takes jobs and provides me more throughput. And also, let's say I change my system A to system G, but because I'm generating the same job, the other system really don't care if that's a system A or system G or some human is generating jobs. Or I can even have a system H that are pumping in jobs into the same pipeline. Other systems don't care. I mean, they still just work as before. So message-based integration, this is not me recommending or Microsoft recommending. Actually, this is a quite commonly acknowledged integration pattern adapted by industry. So whenever you integrate two systems, especially if the systems are on different tech stack, you should consider the message-based integration. And the moment ago, we talked about Windows Azure provides you connectivity between your on-premise network and your Windows Azure network. And here's a little diagram to explain the configuration. So on the right, I have my local network, and I have some machines. And on the Windows Azure, I have a virtual network that I connected with some virtual machines. What you can do is to set up a site-to-site connection, which means you can actually have those machines connected as if they are connected on the same local network. They have the same local network address space. You can ping each other. You can send files to each other. They're just like they are on the same network. And now with Windows Azure virtual network, we are providing point-to-site connection as well, which means for any laptop, after you install a VPN client, you can actually connect to your Windows Azure network from anywhere of the world. I'm going to show you that in a moment. So that's the two major integration offerings, message-based and the virtual network. And how many of you are familiar with Windows Azure Active Directory? Heard about it? Okay, about 1/3. So here I'm just going to go through this quickly. So basically, Windows Azure Active Directory is a directory on the cloud. It helps you to provide authentication of your cloud applications. And what's unique about it, as I just mentioned, you can integrate with your on-premise Active Directory so that you can project your on-premise user credentials to the cloud so that your users, your enterprise users, can log in to their cloud services using their domain accounts. So here I'm going to show you a little animation. Basically, for your application, you configure with Active Directory as a trusted rely-on party, which means I'm relying on Windows Active Directory to do the authentication for me. And when the user tries to access the application, the WAF module got inserted into the application, will intercept that request and sees that the user has not been authenticated. And it will ask the WAD to present your login page. You log in with Windows Active Directory tenant, and the tenant gives you a token back. Then you attach this token to your next request, and this time WAF intercepts the request again and sees, oh, now you're authenticated. So in this way, you can see in your application, you don't need to handle the authentication at all. Basically, you're just outsourcing all the authentication work to Windows Azure Active Directory. Actually, the benefit of doing this may be not apparent in the software environment, but if you take in the real-life example, it should be easier to understand. This is like when you try to lock your front door. Do you make a lock yourself, or do you go to a store and buy a lock? I think most of the people will choose to buy a lock because you know those guys are professionals. They know how to properly make a lock. But in reality, in a lot of systems, what we see is that users try to implement authentication by themselves. And the expectation that unless you are a good lock maker, you can make a decent lock. Otherwise, you should rely on other people who have spent collectively hundreds of years on authentication as their profession and to do things properly for you. And you get that for free. Windows Azure Active Directory is free. There's no charge with Windows Azure subscription. So you should definitely consider to use that. And here I'm going to, that's a single sign-on case. Basically, you can have multiple applications registered with the same tenant. Because they trust the token from the same tenant, you can provide this single sign-on experience so that the user can only needs to sign in once and can access all the trusted applications. And there's a projection from your on-premise AD to your Active Directory. So, gee, I went through that really quickly. Let me take another sip of water. So here comes the fun part. So basically, we've talked about a lot of practices and principles in general. Now I'd like to show you something in the practice. I'm going to show you some specific skills, new features or patterns you can use in your own application. So for this, I'm going to jump into, I think, 3 demos. So the first one is the streamlined diagnostics. Like I said, the general strategy for us to improve reliability is to reduce the mean time to repair. So we provide a lot of diagnostic support for you. And this is one of the examples. Let me log into this machine. And I have 8. Okay. So this is a very simple site I created. This is called a blob album. Basically, it's using blob storage so you can create albums, upload pictures. For instance, if I open the album, you can see the pictures inside. I think I lost my network connection. Okay, it's back. So anyway, it's a very simple application. It's based on Windows Azure Blob storage. Now I'm going to create a new album. I click on the link. I'll just say some name and some description, right? And I say create. And too bad, nothing happened. And there's no error message. It just didn't happen. So apparently there's a bug in my code. So how do I fix that? So I can open up Visual Studio. And in the Server Explorer, now I can actually connect to all my Windows Azure websites. I can expand my website, find my subscription. And this is my website. Just to show you I'm not cheating, you can see the URL is a real website. It's not running on my local machine. So I go to this website and right-click. I say View Streaming Logs in Output Window. I click on that. You can see the output window is here. Now I'm actually connected to my log streams running on my website. What I can do now is to go back to my live site. I just recreate the problem. And say create. Yeah, nothing happened. And go back. And you can see the exception right there. This is I don't need to stop the application or do any additional tricks. I can see because the blob container exists failed. It turns out is that because I'm using because I'm a bad programmer, I guess, because I'm using the blob container name as my album name. So if the user enters a space in the name, then the system is screwed up. Of course, I can fix this, but the key point is that now with this kind of streaming logs, you can quickly identify and fix your problems on your website. So that's the first demo. It will be quick demos. So the second one is to the point-to-site connection. This is how Windows Azure provides your connectivity between your on-premise network and your Windows Azure network. And you can also connect any machines to your Windows Azure networks. Let me switch back to my presentation machine. So in this case, I will show you, I already defined a virtual network. That's my virtual network. And on the virtual network, I've provisioned a virtual machine. This is my virtual network, the point-to-site virtual network. And what I can do here What I can do here are two things. First, I can upload a client certificate. Basically, the certificate is used to authenticate my client. And I can download a VPN client, which is tailored for this specific client. So I already did that. I will just show you. After I installed the VPN client, you will see additional entry in my network. See, this is my VPN connection. You can just click and connect to it. Now I'm connected to the same virtual network. And on the virtual machine, this is my virtual machine. I have created a shared folder. And what's my local IP address? It's 10.0.1.4. So I can open the file browser. I can just say 10.1.4. I can access that share. And actually, I can create a new folder. Let's say log files. And I can even, transient errors. Folder 2. Okay. See, that's why you have to retry. And when I go back to my virtual machine, if I open the share folder, you can see my folder 2 is right there on the machine. So you can see it's really easy to have the laptop to connect your virtual machines on Windows Azure network. So that's the second quick demo. I think for the third one, I'm not going to switch back. The third one, I'm going to show the what we call the competing consumer pattern. Actually, for this one, I do need to switch back. How much time do I have? I think I have time to go through this. For the third demo is the competing consumers pattern. This is a very important pattern because I've seen personally, it's important to me because I've used this pattern to solve a lot of difficult problems. The competing consumer pattern is really useful to solve the global state problem that I just mentioned. For instance, if your system have a global dispatcher, when we approach this problem, the problem is you have a centralized component that control all the connected components. That's the problem. But the way to solve this problem, we can turn it around. Instead of having a central dispatcher, we can have competing consumers to compete for the tasks. And this is how you do it using a Windows Azure Service Bus. So ignore the text. I will just focus on the animation. So in this case, I have a producer and two consumers. What's happening is that the producer will generate some jobs, and the job will be put on the queue. And let's say consumer 1, it wants to handle the job 1. What it does is to place a lock on the first job and handle the first job. And then the consumer 2 comes in at the same time. It places another lock on the second job and handle the second job. What happens is now that consumer 2 finished the job, and the job is removed from the queue. Everything is okay. But consumer 1 actually crashed. And this lock will expire after a certain time window, and this job will reappear on the queue for other consumers to pick up. So in this way, you can actually have this failover scenario that to ensure a job is handled at least once. So in this case, the job reappears, and the consumer 2 picks it up and handles the job. I skipped that slide. The competing consumer pattern is important because A, it's a scaling pattern. You can scale out to multiple consumers as much as you need it. B is a failover pattern. You can achieve failover using competing consumer. If one consumer fails, you can fail over to the other one. 3, it gives you ability to dynamically scale your system without affecting existing components. If you need more throughput, you just add more consumers, or you can remove consumers. Your existing system can keep running. So for that, I'm going to show you I think that's the last demo for today. This one, if you've watched Microsoft events before. You may have seen this. This was a big compute scenario, but I migrate the whole scenario into a Windows Azure worker roles. So basically, in this case, I have a web front end that allows me to take in frame rendering jobs. But in the backend, I have 7 worker role instances. Each of them is only capable of rendering 1 frame at a time. But if I want to render more frames in parallel, I have to scale the system out to multiple instances. So in this setup, I have a single web role, takes in the request. Then I send the job to the queue. Then I have 7 competing consumers to compete for the job. So in this way, I will just create 7 jobs, let's say. I will render frame 10 to 16. Let's say render frames. Basically, here I'm generating 7 jobs, and those jobs are sent to the job queue, and they're waiting the worker roles to pick them up. And apparently, none of the worker role is working right now. I don't know why. Yeah, too bad. It's not rendering. Okay, it may come back later, but we'll just go ahead. Okay, that's the competing consumer. I think that's the last demo. We have to skip this case study because of the hardware failure. But if any of you are interested in such kind of a scenario, you can talk to Sebastian after the session. He's over there. Can you just raise your hand to show people? Okay. Okay, with that, I will skip the demo. Thank you very much. And if there's any, thank you. Thank you. But there's still a couple of housekeeping items I need to do. That's my contact information. If you have more questions, you're welcome to drop by. And there are some other things I don't really know. And you have, but the key point is that to send us back your feedback. This is really important to us, especially if you want to hear more about architecture talks. Reflect that in your feedback value score so that we can do more of these sessions. Thank you very much. Thank you.